Hey everybody. So oftentimes on this channel, I'll go through archive and then I will look at research papers and then on my video, I'll present that research paper that I find intriguing for that day and then talk about that overall, right? But I realize that that doesn't always or ever give the full framework as to exactly what I'm doing, my methodology behind it, etc. Right? And then to me, I can frame up and summarize my methodology behind these things in a very straightforward way. To me, 99% of people that dive into AI dive into the wrong things. They get caught up in the working mechanisms of the LLM model. They don't know how to code is a big one, and then so that's the biggest impediment to start off with there, right? They look at it purely from an engineering perspective, etc. To me, all of this is a mathematics problem. Like it all boils down essentially to mathematics overall, 100%. Like if you ignore the mathematics within this, you won't grasp it. Like that's just the bottom line. I can't put it more simplistically than that. But what I can say within that is that the way that I personally view the mathematics around this is different than how most people do, and I think that's kind of my secret sauce within this, right? To me, math is a subset of logic, which is a subset of philosophy. Like that's the most simplistic way that I can put that, right? And then so when you are dealing with mathematical equations as the end result, that end result equation is the end result process of a philosophical train of thought that comes within it. And it doesn't matter what the research paper is, right? And then so just going through like the first thing that I want to start off with here is just like a general exercise. I'll show you kind of like exactly how I would go about before making a video. Archive from this is Friday, October 3rd. And then just going through papers that have been published today, right? And then I've already gone through, you can see I've already gone through some of these papers, but that's what I do on a daily basis, right? When the papers come out, the ones that intrigue me, I look at them more, and then I take a look. So this one, right, like the unreasonable effectiveness of scaling agents for computer use. And then we click into this one, and then I can just look at the abstract here, and then so computer use agents hold promise for automating everyday digital tasks, but their unreliability and high variance hinder their application to long horizon tasks. We introduced behavior best of n, a method that scales over agents by generating multiple rollouts and selecting among them using behavior narratives that describe their agents' rollouts. It enables both wide exploration and principal trajectory selection, etc. And then they're saying that they score up to 72% compared to state of the art, which is at 69.9% right now. So overall, this method is a method with regards towards scaling of agents, right, and effectiveness of agents overall. And then so that starts off as the general philosophical question, like what exactly is holding back agents at this point, right? And then to me, it's when you break that down on a philosophical level and a philosophical basis, what's known around all of this now is that the failure within current agents is not within the planning phase, it's within the execution phase. And then so anything or any solution would want to fall and be around that execution. And then that's exactly what this, I already know this behavior best of n is all around that execution phase and that execution problem, right? And then so it's this, so taking this research paper and then my broad understanding of this full entire problem, I can apply my philosophical and logical understanding to it to come up with and understand reasonably this paper from just the abstract here, right? And then that particular paper, like there's like that particular paper and that particular framework, that particular philosophical tree, I think has been worked a lot and extensively. But so when I do want to employ, let's say that, I'm in research mode, right? But then I do actually I get a client and it's they want the they want agents, and then they want it to be the best performing and the max performing that can currently exist, etc. I would go back to that research paper there, right? Because that research paper, they're showing that they're beating state of the art, and then so that would be a good example and a good framework to build off of. I would build off of that framework, test it out, make sure that I could verify their claim within that, and then if I could, then that's the framework that I would present to a client in that particular instance, if that was their very specific narrow goal, right? And then in that I would show and I would prove out that it's beating any other state-of-the-art solution that they would want to go with. And then so just diving into like some of these other research papers, right? So next one that I clicked on here is the reasoning boundary paradox, how reinforcement learning constrains language models. And I won't dive into each one of these ones, but so this one very specifically, anything around, and I know this one's all around like RLVR, reinforcement learning with verifiable rewards, and that kind of damages the models and then creates boundaries and limitations in and of itself. That's what this paper went into, right? And then I know that just again by going through the abstract and then clicking and then looking through the paper there. This one caught my eye here too, constrained adaptive rejection sampling. And then I think this one was like, so this one's kind of like, and that's kind of what happens when you go through and you look at these papers and you go through them, right? Because to me, this one has actually like kind of like a correlation to this one in that they're kind of tackling like two sides of the same coin, or one of them's presenting the problem and one of them is the solution. And that happens a lot when you look through and you actually read through these research papers like this, right? And then next one, the last one I'll focus on here is this one, Metabot, AI-based agent for natural language-based interaction with metabolomics knowledge graphs. And I'm like, so this is all dealing with the like medical field and like diagnoses and discoveries within that, but then they're utilizing knowledge graphs and then the technology and what they go off of and what they research off of. It's easy for me again to like take a look at their framework, understand exactly what their framework is doing, and then I could easily just like apply this to other areas beyond this metabolomics, right? I wouldn't need it just for that specifically, and then like especially like with what they're dealing with knowledge graphs, etc. I could deal and do a lot of different things within that, and then that like so understanding like the difference between like knowledge graphs, between KNNs, between a Monte Carlo algorithm, etc. Like those are where the understanding and the major advantage comes in when you're actually building out AI, right? So like the most simplistic framing that I can give you off the top, we're going to dive into like the actual algorithms here now, but before that is the framing I want you to have in your head is essentially that every company that is in existence right now when it comes to AI is a wrapper company, unless they're like literally like OpenAI, not Microsoft. Microsoft is a wrapper company. Facebook, Meta right now is a wrapper company, etc. Right? And then being a wrapper company just means that you're not focusing on the models, right? They're like I would say that Meta is the best wrapper company that is currently in existence. They're putting out very high quality research. They're changing the game, moving things forward within that area, right? Putting out brand new algorithms like all of the time because they bought out a bunch of that talent, right? But so within that and understanding that, like that term wrapper is applicable. Even OpenAI is 90% a wrapper company, right? Essentially, you have a model and then you're building algorithms on top of the model, and then what is the big determination within that? What matters is that if my algorithm that I have wrapped around my LLM model is better mathematically than your algorithm that you have wrapped around your LLM model, I'm going to win. Like that's the part of this that most people don't understand, right? They think that it's just ChatGPT or the model is evening of the playing field, which is true, right? So then if like 90% of the world is operating off of ChatGPT, but if I'm operating off of ChatGPT plus a bunch of algorithms wrapped around that, I'm significantly, and it's like 30, 40, 50% increasing the performance of that model, right? And then you can call it a wrapper, you can call it algorithms, you can call it whatever you want around that, but understanding and playing around with it On that level is where the difference comes in, right? And then at that's where it's like I look at it kind of, it's like Harry Potter, right? Essentially, like you're creating and then crafting this algorithm, framework, model, etc., which is all that you're doing, and you should be planning all of that out up front, right? That's the biggest thing that people fail at within AI. Like, why do they fail at AI? Because they don't approach it from this proper mindset, right? And then so with that, let's dive into this deeper, right? So I want to dive deep into building AI algorithms, a philosophical approach for everyone. And then so as an introduction here, math as executed as philosophy. An algorithm is simply a logical argument that a computer executes step by step. Just as a philosopher constructs an argument about truth or morality, you construct an algorithm about patterns, predictions, or decisions. When you write the equation, for example, if x is greater than 5, then y equals 10, you're not just computing, you're making a logical claim. And the logical claim within that particular equation is, given this condition, this consequence follows. AI algorithms are collections of such claims, working together to reason about data. And I'll dive deeper into it within this, right? The philosophical foundation. So what is an algorithm? An algorithm is a recipe for reasoning. It takes inputs, which are observations about the world, and applies logical observations, which are your philosophical principles, and produces an output, a conclusion or actions. So think of it this way. Traditional philosophy would be all humans are mortal, Socrates is human, therefore Socrates is mortal. Whereas an algorithm would just be all emails with these words are spam. This email has these words, therefore this email is spam. And so the core question of AI algorithms ask, how can we make machines learn patterns from experience rather than following only rules that we explicitly program? And this is what I want to dive into, right? So this is fundamentally a question about epistemology. How do we know what we know? And can machines develop knowledge the way that humans do? And then so when we talk about this and we tackle this from a epistemological foundation, there's an important element that is very important to understand within this, right? And it's, I've stated this before, but I don't think people understand the gravitas of it overall, right? So in my philosophical worldview, and at least as it applies to AI as a whole, there is no such thing as a big T truth that exists in the universe, right? Big T truth is not a concept, and it's not a concept that can be boiled down into data. And then so what does that mean very specifically? Like the best example that I can give around that is lottery numbers, right? And then to me, it just very clearly paints that picture. And then so if I give you the winning lottery numbers for yesterday, that's absolutely worthless to you, right? If I give you the winning lottery numbers for tomorrow, that's a universe of a difference. And then, but the difference between the winning lottery numbers yesterday and tomorrow, there's no big T truth in that. It's just 2 days difference, right? The only value, the only truth that is inherent within that is the truth that you assign to it. You and me as a human, there's a lot more assigned value to the lottery numbers for tomorrow than for the lottery numbers for yesterday. But on a universal scale, a universal perspective, there is no actual truth within that, right? And then so that's beyond important when it comes to dealing with AI and these algorithms, because that is the core foundation, like rule number one when dealing with algorithms for these models to learn, right? We are creating algorithms for these models to search for truth when there is no such concept as a big T truth that exists within the data set. And then so understanding that up front, you know that every single thing that follows has to be couched within that. And then when you break it down from that aspect, that's all AI does from that aspect, right? So from there, once you have that particular framing, there's only so many different ways that you can break the data up, right? You can classify it, you can predict off of it, or you can generate off of it. And that's really it. Like there's no other buckets that fit within that larger framework, right? And then so with that said, that kind of brings us directly to the logic behind AI algorithms. And then so I want to start off with the three philosophical principles or pillars of the logic behind this. And the first one is representation or ontology, which is how do we represent the world in a form that computers can actually process. So an example is to teach AI about cats, we might represent those cats as, we can represent it in different ways, right? We can represent it as a collection of pixels. We can represent it as sets of features, like does it have whiskers, ears, or fur. We can do it via like the relationships between the parts, like a cat versus a kitten, etc. And then so your choice here embodies a philosophical stance. Like no matter which one of these you choose, you're making a philosophical statement the second that you choose that one, right? And then so that stance is essentially you're saying, in this instance, my philosophical stance is that the essence of catness can be defined purely by a collection of pixels, or the essence of catness can be purely defined by a cat's features. And then from there, you're either right or wrong with that philosophical assumption, right? And then the second aspect of this is learning or induction, which is how do we generalize from specific examples to universal principles? So how do we get from those specific examples to a projection, a semblance of a truth within this data set? And then so this is a classic problem of induction. If we show an AI 1,000 pictures of cats, why should it recognize the 1,001st? This is exactly what David Hume argued about human reasoning, right? That's kind of the way that human reasoning processes in like a hierarchical deductive order that will essentially inductive get you to that what would be that 1,001st problem, right? And then the third is optimization or teleology, which is what goal are we trying to achieve and how do we get closer to it? So every AI algorithm has a purpose, a good that it's trying to maximize, and then this ethics is encoded as math, right? And then that's whatever its reward function is what it tries to maximize. And then within that, like it's inescapable to put ethics within that, right? Like you have to at some point within that input ethics within in that particular philosophical framework, right? Because you're dealing with philosophy. I can tell you flat, like I don't feel that I'm the arbiter at all that ever should be putting ethics into a model. Like I hate it, right? But like you have, like, I mean, I don't have a choice, right? I wish that society were constructed differently, where more people understood this and realized that people have to make that choice when building out these models. And then so what's the choice that I make? I default to natural ethics in all of this, just flat out, right? Like then like no beating around the bush, natural ethics followed by utilitarianism. And then utilitarianism is actually a good framework for these models because you can backpropagate, and then so it solves a lot of the real world problems of utilitarianism. But if you don't like that, natural ethics and utilitarianism, then I mean that's we should have more discussions around these things, right? But so there it is. And then so part 3 is how to build AI algorithms. Step 1 is to define your logical claim. So start with the philosophical question. What pattern am I trying to discover, or what decision am I trying to make? Examples of that would be, I claim that house prices depend on size, location, and age. I claim that customer purchases follow patterns based on browsing history, or I claim that medical images contain detectable signs of disease. So up front, you're making a logical claim or a logical assumption that you can take this data and classify, predict, or generate off of it based off of having enough, what it would be enough of that data to satisfy your framework. And then so step 2 within that is choosing your representation. Like how exactly you're going to encode that world into numbers, right? So you take your philosophical claim, and then we need to make that into into an actual structured logical argument utilizing the human symbols of mathematics in this instance to be able to structure that framework. So that's your step 2 is building out that full mathematical framework, right? And then so for structured data, you utilize spreadsheets and databases, and then so each row is an observation, each column is a feature, like which is a property that you think matters, and then so this becomes your ontology, your claim about what exists and what's relevant is that entire structured spreadsheet of data that you end up building out for the model. For images, it's pixels as numbers, literally like between everything is represented as between 0 and 255 on brightness, and then or you can utilize extraction features like edges, colors, and shapes. Within this and within that, you're claiming that these properties capture the essence. And then so like when you're training a classification model on images of cats, you're taking those images, you're deconstructing, you're compressing them into a 2D image, and then each one has different edges, colors, shapes, and brightness, right? And then so you're just literally like what you're telling the model then is that the essence of catness can be captured within brightness, edges, colors, and shapes. And then the model's not looking at anything else. Like it's not looking at the whiskers unless you're saying like classify via the features of the cat, and then that would be a different classification, right? And then so for text, you're doing the same exact thing. So words are vectors and meaning space, and then they're essentially like counting things like frequency count, right? Like that's like my big problem is always been with tokenization as a whole is that the process is so lossy it isn't even funny, right? Like one of the biggest algorithms that exists and the most common algorithm within word vectorization is called bag of words, which is just literally a frequency count, right? So if it's if I have a sentence, the cat sat on the mat, the frequency count or the bag of words vectorization for that sentence would literally just be like 1 1 1 1 1 2, and then the 2 would be the, right? Because the appears twice and the cat sat on the mat, but every other word only appears once. So every other word is a 1 and then there's a 2 in there, and then that's literally all that the model gets. Like it doesn't get any of that meaning, any of those words. It's just 1 1 1 1 1 2, and then somehow it works from that, right? But then so within that, and then how it works and why it works, and then why you're doing it is that you're claiming that language has a mathematical structure to it, and that's that mathematical structure, just feeding that mathematical structure, that projection, that representation is enough for the model to actually work because of that underlying mathematical structure. Step 3 within that then is that you select your actual algorithm, right? So this is where you choose your logical inference method, and then you've got a wide variety of choices within this. You can go with linear models, decision trees, or neural networks, and then any combination or substructure within all of those, right? And then you also have ensemble methods, which are like collective methods. So bringing multiple methods together via different, like a whole bunch of multiplicities and different frameworks overall. And then this is kind of that meat and the sauce, and then the understanding of AI models and the math behind this overall, right? Like, so the most simplistic way that I want to break down within these things is, so when you're dealing with like pure linear models, you're like, this framework and these models operate purely off of an algebraic equation, right? So when you're dealing with linear models, you're dealing with linear algebra, and then so there's no direct probability within a linear model. Where you get the probability from, and same thing, like can be the same thing with decision trees. You can inject probability into decision trees, but you get major probability here, right? And then so generally speaking, with your more complex models, you're combining several linear models, maybe a decision trees model, and then a neural networks model. So then you're combining these linear approaches with these non-linear approaches and these probabilistic approaches, and then it's that blend overall, right? And then the blend becomes how probabilistic is your model, and then there's a direct trade-off between probability and linearity that you always know up front plugging into these equations, right? Like if you want your model to be more generalizable, to go further and further away from the training data set, you know that you're going to have to increase the probability within the algorithm that you're building out. But you also know within that if you increase the probability of the algorithm that you're building out, you're decreasing your ability to guarantee accuracy. And then so that's the trade-off, right? And then so you have to work through within that and then find the balance, the equilibrium, and what actually works within that mathematically. And then some things work mathematically far better than others do, right? That's just how math works overall. And then so step 4 within that, so once you've got, like, I'm going to use this class of algorithm, you have to define your objective function. So this is your ethics, right? What counts as actually good. So for prediction problems, you're minimizing the difference between my predictions and reality. So for classification, you're maximizing the correct categorizations. So for generalization, you're maximizing coherence and relevance. And then the most common objection functions would be mean squared error or cross entropy. And then you can also build out custom objectives. But then, so this is kind of like how you're going to measure the success of your framework overall, right? Is the bottom line within that. And then step 5, once you got your measurement for success, then you actually implement it. You put it into real world terms. And then so that's optimizing through iteration. And then so this is the execution phase, repeatedly adjusting your parameters to improve performance. And then within that, the most common method that you utilize within AI at the moment is stochastic gradient descent, right? That's the most common method. And stochastic gradient descent is the entire reward function for the model. And literally, like, this is like, understanding this concept will make you understand AI more generally as a whole. And then, like, a lot of people try to say, like, they think that these things are just the most complex thing in the universe, right? That this is just so far advanced, I would never be able to understand it or understand what is exactly actually going on behind the hood. And or they get to this, they realize this, and they're like, there's no way that it's that simple. A baby could have come up with stochastic gradient descent. Like, not to knock it in any way, right? But it's like, so literally, like, this is what stochastic gradient descent does, right? And this is the literally how it works. The first step is that you calculate. So if I change this parameter slightly, does my error increase or decrease? And then so it's you pass an input through the model. Let's say that you're trying to get the model to guess the number 10 between numbers 1 and 10, and then its first guess is 5, and then so you run it again, and then its second guess is 4. Is 4 closer or further than 10? In this instance, than 5 to 10. In this instance, 4 would be further. So we increase the error with our second pass through. So then the next step in that is that you adjust. You move in the direction that the error decreases. That's literally it, right? So then on our scale of 1 through 10, our first model calculated 5, our second model calculated 4. So then we tell the model via stochastic gradient descent, move in the exact opposite direction of whatever you did to calculate 4 instead of 5. And then it's going to do that. And then the next result should be that it outputs 6 because it moved in the exact opposite direction. And then we say, okay, good. Keep moving in that direction. And then maybe it hits a hill or something goes off and wonky on that. And then it's like, its next response is like 5.4. And then like, okay, you messed up a little bit. Let's rerun that back. Whatever you did to get from that 6 to that 5.4, I don't know what you did, right? But just go the exact opposite way, bro. Like whatever, like you went this way, just go that way. And that's literally what stochastic gradient descent is. Like there's nothing more complicated to it than that. Part 4, how to evaluate algorithms. So the problem of overfitting, mistaking memorization for understanding. This is a big problem, right? So your algorithm might learn every training example with exactly these features has this label. But this is like a student memorizing specific exam questions rather than understanding principles. They fail on any new questions, they just memorize the answers, right? And then so the philosophical insight of this is that true knowledge generalizes beyond the specific instances that we've seen. This is the difference between wisdom and mere memory. And then you can detect this very easily, right? People are like, well, like, how do you know? Like, so, like they a lot of times too, they'll like try to throw out like, oh, that's just overfitting without understanding these concepts at all, right? But so generally speaking, how you do it and how you detect it is, so when you're training a model, you do a train test split, right? Where you split the data set 80-20. 80% of it is your training data, 20% is your test data. And that 20% the model never sees or is never trained on. And then you measure training accuracy and test accuracy. And then this is where you 100% know if the model's overfitting, right? Because if there's a big spread, a big gulf between training accuracy and test accuracy, the model's overfitting. It's just literally memorizing the data set. So like if you have a training accuracy of 99%, but your test accuracy is 60%, it's just memorizing the answers. And then so you can also use cross-validation tests, so test on multiple different splits, right? Like and change out that split, etc. And then also generally speaking, then from there you have the concept of, you can also have the concept of underfitting. Underfitting is a far less problem than underfitting, but generally speaking, you'll just have high error rates across the board, right? And then within this, there's like actual mathematical ways that you can actually measure these things out, right? They're pure calculations that you can do on your data set, and these are all like across the board. You can measure mean squared error, R error, accuracy percentage, precision, recall, F1 score, top K accuracy. You see these like all the time, etc., right? And these are just like essentially measurements and checks, like how well is this model actually like performing? Is it actually like is there overfitting, etc., going on? And then if you see like, if they're measuring these numbers, like you can reasonably tell from these numbers, right? And then just look at it from there and make assumptions from there. And then part 5 of this is like the art of algorithm selection, right? So that's kind of the biggest thing within this. So at the top, I mentioned that there's different subsections of the framework that you can do once you understand the framework, right? You can classify, predict, or generate. And then within those, you have different types of algorithms, subsets of algorithms, and then you have different problems that exist around these things, right? Like, and so you could have like limited data, a lot of data. You have a lot of linear relationships, a lot of like transformations needed, a lot of tabular data. Whatever the situation is, in those individual situations, to solve those individual problems, it's going to be a different algorithm to solve those individual problems. And then when you're building out a wrapper, we'll call it, you're essentially building out a solution to solve, let's say, like a group of like 5 or 6 of these different problems, right? And like this is the other area where people fail within this, right? Is so they're able to like identify those like 5 or 6 unique problems. They build out the framework for it, and then they just throw like ChatGPT at like all 5 or 6 problems, and it's like, well, okay, let's take a look at these, right? Like 2 of these are linear regression problems, which like ChatGPT is gonna like blow chunks at linear regression problems. Like just throw something simple in there. One of them is one where we can just put a simple decision tree in there, and then like ChatGPT would be good at decision trees. Like that's not its weak point, but it like ChatGPT would be 1,000x more expensive than a simple decision tree within that process, right? And if I'm doing this process 1,000 times or 10,000 or 1,000,000 times, why not just put that simple decision tree in there up front for that one part of the process? And it would actually be more accurate. Like it's like there's no downside to putting that decision tree in there, right? It's just a matter of knowing that it exists to put in there overall. And then the last parts of this are just like practical steps, and then kind of like if you want to dive deeper into reading around this, right? So I'll leave that up to you, and you can read through this. So the last thing that I want to illustrate with this and show this to you up front. So to me, like I wanted to give you kind of like, this is my how I do this and apply this in terms of like my real world everyday like going through and studying these things. But then so like how do I actually like employ these things and put these things into practice, right? And then so I just made like this is a concept that I've been kicking around in my head for a while now, right? And then so very specifically and simplistically, this is a unique algorithm that I built out and I've started testing, which is I'm testing a chemical reward function versus plain stochastic gradient descent. And then so in my mind and how I look at these things is that the human reward function, what I'll call it, is significantly more complex than the AI reward function. The AI reward function is literally stochastic gradient descent and variants of that, whether it be like Atom W. Those are like the two biggest ones that ever exist, right? And then that's it. But the human reward function to me is a chemical process and a blending of chemicals, which like why people can have like chemical imbalances, etc., is because it's those chemicals are what's responsible for blending and making sure that reward function is can have like a multiplicity of inputs for the reward function and competing inputs. And then so I figure like I want that for a model as opposed to just, hey, go the other way, right? And then so I want to test that out and see if that works. So that's my framework. I have my framework in mind. That's my framework is that there's a possibility that chemical reactions would be far better than just, hey, bro, go the other way. And then so I want to test that hypothesis. I need to create mathematical formulae, and I went through that. And then essentially like how I want to build this out, how I want the chemicals to be represented, etc. Right? And then so within that, the next thing I do is that implementation phase, right? So I build out a toy model in this instance, which is just like grid world, like a 10 by 10 grid. And then we have our environment, and the grid randomly updates so that the model can't just memorize it. And then I go through, and then this is essentially like where I'm giving it its policy, right? So I'm making it, and I'm just taking like a simple multi-layer perceptron, and this like the most simplistic multi-layer perceptron that I can, and I'm just giving it like chemical agents around it, right? So I'm taking this multi-layer perceptron and I'm creating a wrapper out of it, and then my wrapper in this instance is my chemical agents, and then like within that I have like essentially two cells of math within that. Like this is my primary math, right? But then so all of those things that I did in those previous steps to build out the mathematical framework, constructed, etc. Here it is right now, and then so now I have, this is like what essentially like how the chemical equation works, right? And then you can see here like it's the chemical controller state, and then so that's like I'm wrapping this chemical controller state around the stochastic gradient descent function, and then same thing here, I have to train it, right? And then so I have to like, and then I'm further like I'm taking a lot of these regular measurements that you would take within the model, like temperature, distance, etc., but then I'm turning them into chemical equations, chemical processes via the philosophical mathematical framework that I built out to test this. And then I get chemical-based tuples, right? And then so that's essentially how I'm doing this and building these out and building these into the reward function. And then so I'm just taking like the end philosophical concept and then making the math fit within it. And then so within this, and then I test out my very first iteration. And then what we can see here from this baseline iteration is that I'm getting like, so like this like is, it's not 100% like a perfect match 0, right? Which is good. And then I'm getting like some differentiation here, which is good as well, which means that like there's this process is actually working. And then what I know within this is that like this is intentionally minimal, right? And then so this chemical controller is a PID style homeostatic loop, not full meta gradients. It's enough to demonstrate dynamics, and that's kind of just the bottom line within this. Right? Like it's at this point a very simplistically modified stochastic gradient descent function, but that's what I wanted and what I needed to as step 1 of my framework within testing of these things. And then all of this entire creation is based off of philosophical and then therefore mathematical principles that I'm guiding it and trying to gear towards within this, right? Not just like throwing like random stuff at a wall to see what sticks. It's like, okay, I think that a chemical reward function would be better than SUD, and I start from there, et cetera, and build out, right? Exactly as I described. And then so once you like get down to that and understanding of that, that's what all of this is, right? Is taking these different frameworks and then either dissecting them and understanding them and using them holistically as they are, and then applying them, or making modifications off of them and around them that you know will work out based off of past experience, etc. Compute efficiency, the unique problem in and of itself, etc. And then that becomes your models that you build out, and then that's where you are at the end of the day, and that's where all of the algorithms come in. And then so hopefully this gives you a better understanding from when you started as to the importance of algorithms overall within this equation. I'll leave a link to both the doc here as well as the Scholar notebook. If you want to go to archive, it's just archive.org, and then you can check it out there. And if you like this type of content, please like and subscribe. Thank you very much.